Crystalline structures. First, we will define what a crystal lattice is and talk about the basic cell types that make up these crystal structures. For each of these, we will discuss how many atoms make up the geometry, how to determine the size of the cell, or the atomic radius, and we'll also discuss how to determine the unit cell from the given information. Crystal lattices are repeating regular arrangements of atoms. The smallest unit required to repeat the pattern is called a unit cell. There are several types of unit cells. We're going to focus on simple cubic, body-centered cubic, and face-centered cubic, and then we'll cover a very small amount of close-packed structures as well. A simple cubic cell, as it sounds, is the simplest of the cells. It has one atom on each corner of a cube. For each of these cells, we will discuss how many atoms per unit cell, the edge length and the unit cell, the edge length of the unit cell, and the coordination number of the atoms in the cell. For a simple cubic cell, when determining how many atoms per cell, we're going to look at each atom. Note that the atoms are part of the unit cells around them as well. This figure will help you visualize that. This means that each of the 8 atoms will only donate 1/8 of themselves to each unit cell. Here I've drawn out an 8-unit cell picture to help you see this. Notice how the middle one is split between all 8 cells. This is happening on all sides of the atoms, of course, as well. I just only drew out 8 because it can get rather complicated looking otherwise. So this gives us 1/8 per cell times 8 atoms is equal to 1 atom per cell. Now, coordination number is the number of atoms that an atom is in direct contact with, and this varies for each of the types of cells. Here I have our 8-unit cells drawn again. We'll focus on the middle one since we can see all of the unit cells around that middle one. To figure out the coordination number, you need to use the number of atoms that are in direct contact with it. So let's remove the atoms that are not in contact with the ones that you see, and that's what I have in the second figure here. So now you can more easily count around the pink atom that I have accentuated. So there are 6 atoms in direct contact. Now this would be true for all of the other ones as well if you were to keep drawing out the unit cells and draw, 16 or 32. This gives us a coordination number for a simple cubic unit cell of 6. The edge length of each unit cell is determined by the geometry of its cube. In a simple unit cell case, the atoms on the corner are in direct contact with each other. So take a note of that before moving on. Now we can look at the geometry and say that the edge length of the unit cell must be 2 radii, or 2r. So we would write this formula as L, or the edge length, is equal to 2r. A body-centered cubic cell, so this is different from simple cubic cell, but a body-centered cubic cell can be visualized as a cube with atoms on each corner and 1 in the middle. So I've taken the one in the middle and changed the color just so that you can more easily see it. We can count the atoms per unit cell the same as what we did for the simple cubic. The blue ones each have 1/8 within the unit cell. And so it's 1/8 multiplied by 8 is equal to 1 of the blue atoms. For the pink one, it is in the center, and so it belongs solely to that unit cell. It is not shared amongst the neighboring unit cells at all, and so that one contributes 1. So this will give us 1/8 times 8, which is equal to 1, plus 1 is equal to 2 atoms per unit cell. In this case, the particulars of the geometries let us figure out the coordination number by actually just looking at the one cell. And if you were to expand this out to 8 cells, you would be able to do the same that we're going to do for the pink for the blue ones as well. So the center atom here is in direct contact with all 8 of the blue atoms. This gives us a coordination number of 8. We could do the same thing with the simple cubic cell as we did with the simple cubic cell and expand it out to 8 cells to show the blue atoms also have a coordination number of 8. But I'm going to leave that to you to do as an exercise, either by looking up in your book or doing it yourself if you want. Now let's talk about the geometry and the edge length of the body-centered cubic. The geometry of this is far more complicated because the atoms on the edges are not touching each other. The only atoms touching each other run along the diagonal through the 2 corner atoms and the center pink one. This means that we have to do some complex geometrical derivations to get the edge length of L. This is a fairly long proof, and one that if you are interested in, you can look at in more detail in the book, but it's not particularly important to be able to repeat it. So we're going to really quickly work through the geometry once to get our final answer, and that's going to be our important part. So here I have the basic concept drawn out, where we have the C running through the 2 corner blue atoms and the 1 center pink atom. And we can use a series of Pythagorean theorems. So C is equal to B squared plus L squared, where B is the diagonal on one face, so that is equal to L squared plus L squared. Those are both Pythagorean theorems. We can then fill in the B squared is equal to 2L squared into the C squared is equal to B squared plus L squared, which gives us that C is equal to 4R. We can figure out the algebra, work through the algebra to solve for L, and we get L is equal to 4R over the square root of 3. Now, in reality, you would not work out this whole derivation. You would simply use the derivation that's given here, and you would fill in R to get L, or you would fill in L to get R. Now let's switch to the last of the 3 that we're going to focus on. Let's talk about face-centered cubic unit cell. These, as the name implies, have a cubic unit cell, but on each face is another atom. The atoms per unit cell can be figured out in a similar fashion to before. The blue atoms that are on the corner, as before, are each worth 1/8 because they are shared between 8 cells. So there are 8 of them, each worth 1/8. So that is equal to 1 blue atom total. For the faces, which I've colored in the pink color, they are only shared between 2 unit cells, and that's because there's half in one and half in the other. And so each atom donates 1/2 of itself to each cell. There are 6 of these face-centered atoms, and this gives us 1/2 times by 6 is equal to 3. So a total of 4 atoms per unit cell, 1 from the blue, 3 from the pink. The face-centered cubic cell has a much harder to visualize coordination number, especially when you're dealing with a 2-dimensional model on a screen. So we'll walk through this by picking an atom and visualize the atoms that are around it. You may find it easiest to visualize what one is in the middle, even though it's actually very difficult to see in this picture, and visualize what that has around it. You could also visualize one of the face atoms that you can see easily here, count the half that you can see here, and then extrapolate the answer to another cubic or another unit cell that would be on top of it. In either case, if you have visualized all of this correctly, you'll find that the coordination number is 12. Again, this is very difficult to do here, and my suggestion is actually to come into my office where I have models of these. You can also find different things online that will let you sort of 3-dimensionally on a screen rotate them and highlight certain atoms, and that's probably a good way to do it here. But just for completeness sake, here I will state that it is 12. The coordination number of a face-centered cubic unit cell is 12. The geometry for this is also a little bit complicated, although not as bad as the last one. We have to recognize that across one side is the relationship related to R. So across this face is 4 radii, because there's 2 of the pink radii, or its diameter, and then 2 of the blue radii, 1 on each corner. Now that's also related to the edge length by Pythagorean's theorem. From here, we can do the appropriate algebra of b squared, our hypotenuse, is equal to L squared plus L squared, which is equal to 2L squared. So we solve for b is equal to 4R, we fill that in, do our algebra rearrangement, and we get L is equal to 2 square root of 2R. Now I do want to point something out here, and I wrote this like this on purpose because this is how it is written in the book. It is generally written as 2 square root of 2R. And it's very easy to think that that R is inside the square root, but it is not. It's written like this because the 2 square root of 2 is taken as one number. But it's 2 square root of 2 as a number multiplied by R. Do not put the R in the square root. In review, we have covered simple cubic, body-centered cubic, and face-centered cubic. A simple cubic structure has 1 atom per unit cell and a coordination number of 6. A body-centered cubic cell has 2 atoms per cell and a coordination number of 8. And a face-centered cubic cell has 4 atoms per unit cell and a coordination number of 12. We also know the edge length formulas for each of these and can use that to solve for edge length or radii depending on what we're given.